Hey everybody, welcome to our final lesson all about the periodic table. This lesson is really short, so I'm going to use it for really two purposes. I'm going to use it to talk about our last trend, which is metallic character, but then I'm also going to use it just as a general overarching review of the periodic table, and I'll try to do that as quickly as I possibly can. Okay, so let's dig in. So we have metallic character, okay? And so metallic character by definition, kind of annoying, right? It involves the word metal, but it's used to describe the set of chemical properties that are typically associated with elements classified as metals. So what do we mean by that? Well, essentially metallic character is how much like a metal something behaves. Okay, if that makes any sense at all. So when we say that, I want to jot that question down. So like, how much like a metal a substance behaves. Okay, and up to this point, we really have only learned very few things about metals, particularly that metals are going to lose their electrons. Okay, and that's key. That's really the property that metallic character focuses on, is the ability of an atom to lose an electron. Okay, so the ability of an atom to lose an electron. And so what allows metals to lose electrons? Okay, what is it that causes a metal to lose an electron? And to answer this, we again are going to revisit those periodic properties that we talked about. So again, in order to lose an electron, okay, we need to have a low electronegativity value and a low ionization energy value, okay? So metallic character is really substances that have low, based on substances that have low ionization energy and low electronegativity. Let's dig into that just a little bit more. So this idea of low ionization energy, remember that it is favorable or favored to have low ionization energy if electrons are being removed, okay? We as chemists like to use as little energy as possible. I always say this, we're lazy, but it works for a lot, because if we're talking about things being stable and talking about things being favored, we really want to utilize as low energy as possible, okay? So it's favored to have low ionization energy if electrons are being removed. We want to use as little energy as possible, okay? And therefore, okay, what about electronegativity? Okay, so if we're looking at electronegativity, okay, we want there to be low electronegativity. Now think about what that is defined as. It's defined as the ability to attract an electron. So if something is going to behave metallic, it's not going to attract electrons, it's going to lose them. And so we want low electronegativity because metals lose, okay, they do not attract electrons, okay? And so if we're thinking about the metallic character trend, we can use these concepts of low ionization energy and low electronegativity to follow or to give us our general metallic character trend. So I'm actually, just to keep everything on this one sheet, I'm going to put the metallic character trends up top. So let's go ahead and think about that. So let's talk about as we go down a group. So as we go down a group, what do you think is going to happen to our metallic character? So think about it. Let's start with just group one. We start with lithium up top and we end all the way down at francium. From lithium to francium, what happens to our ionization energy? Well, who has an easier time losing that electron? Okay, and the answer is that francium has an easier time losing that electron. Why is that the case? Again, we talked about this a lot in class the past couple days, but the bigger the atom is, the further away that valence electron is from the nuclear pole, and therefore it's much easier to remove that electron. So as we go down a group, our ionization energy is going to decrease, which is good for metallic character. Now, what about electronegativity? Same explanation. As we go from top to bottom, our electronegativity is also decreasing. Why is that the case? Again, the bigger the atom, the less nuclear pull a random electron floating around would feel. Okay, so it has a much harder time accepting an electron or attracting an electron. So as we go down a group, our metallic character is going to increase. Metallic character increases, okay? And as we go across a period, let's think about the trend that way, okay? So as we go from left to right, let's say we're going from lithium to neon, okay? Now, this one's a little bit easier to understand. I'm going to talk about it in trends, and then I'll talk about the shortcut way, okay? But if we're going from lithium to neon, what's happening to our ionization energy? Well, if we're going from the left to the right, what's increasing? Our nuclear charge is increasing, and the number of shielding electrons stays the same. So that means that that extra positive nucleus now is being shielded by the same number of electrons, and it makes it harder to remove an electron, or it requires more energy to remove that electron. So in this instance, as we go across a period, the ionization energy is getting higher. Is that what we think, or is that how a metal behaves? No, okay, that's not how the metal behaves. What about electronegativity? As we go from left to right, our electronegativity is also increasing. The ability of the non-metal atoms to gain an electron is much higher. So again, that's not metallic at all. So as we go across a period, the metallic character is decreasing, okay? And here's the shortcut way of thinking about it, the easiest way to think about at least that trend. We're moving from, if you think about it, every element on the left side of the table is a metal, going over to the non-metals on the right side. So what do we predict would be true if we're talking about metallic character? Well, metals are always going to be more metallic than non-metals, okay? So now, we've talked about metallic character. I want to just take some time to talk a little bit about the summary of everything we've learned here about periodic table. And in order to do this, I want to put everything in one spot, which I think is beneficial for you all as well. Okay, so if you are not following along by using my guided notes sheets, again, that's totally fine. But I would definitely recommend either sketching or finding a periodic table and just kind of taking it and putting it with arrows like I did here. So talking about the trend from top to bottom and from left to right, okay? So let's start with all of our trend, or let's start with our atomic radius trend, okay? Or actually, let's start with an even more broad understanding of the table, okay? So on your periodic table, we have a staircase. This staircase separates the metals from the non-metals, right? Okay, and so again, a majority of our periodic table is composed of metals. Okay, we find those metals on the left-hand side of the periodic table, or of the staircase, right? So anything to the left-hand side of the staircase is a metal, okay? Anything to the right-hand side is considered a non-metal. Now, there are some of those tricky metalloids or semi-metals that fall on the staircase. I'm going to color code those in yellow here. Again, there are two exceptions on the staircase, aluminum and polonium. But boron is a semi-metal, silicon is a semi-metal, germanium is a semi-metal, arsenic is a semi-metal, antimony is a semi-metal, or tellurium is a semi-metal. And again, these are the metalloids. So I'm going to just star and call these semi-metals or metalloids. There are plenty of other really special groups that you need to know the names of. Again, just a really quick review. I'm not even going to write them down, but group number 1 is the alkali metals. Group number 2 is the alkaline earth metals. Groups 3 through 11, that goes up to copper. These are the transition metals. Group 17 are the halogens, and group 18 are the noble gases. And those are the ones that you are responsible for knowing. So I would definitely, if you don't have those written down, you should definitely write those down up top on your new cheat sheet. Like I would make this your new cheat sheet for this whole unit, okay? Now let's talk about trends. Okay, the first trend that we talked about is atomic radius, okay? So as we go, so we're gonna use this for the groups discussion over here on this side. Okay, so as we go down a group, okay, the atomic radius increases. And why, again, is that the case? Well, okay, as you go from top to bottom, there's an increase in the number of electron shells. Okay, and let's talk about the periods. So as you go from left to right, so we'll do periods down here on the bottom. So as you go from left to right across a period, okay, your atomic radius decreases. And again, how do we remember that? Or what is really the cause of that? Again, that's due to increased number of protons or increased effective nuclear charge. Okay, same shielding electrons. Same shielding electrons. You should write out that full statement. I'm just covered by the recording of my picture, so I can't write on top of that. And again, I like to always joke that there's the atomic radius penguin. Okay, this helps me remember that general trend, even if I can't really remember explaining how and why. Okay, as we go from top to bottom, it gets bigger. And as we go from left to right, we get its beak and it gets smaller. And I don't know, you could add an eye or whatever, but that's our atomic radius penguin. Okay, all right, let's talk about our next trend, which is ionization energy. Okay, and again, ionization energy is defined as the amount of energy it takes to remove an electron. So as you go down a group, okay, the ionization energy is going to decrease. Look at me go here. It's opposite of the atomic radius. Okay, ionization energy decreases. Why is that the case? Again, that's the case because increase in atomic radius, okay, means that there are more shielding electrons. And it's easier to remove an electron if there are more electrons in the way of blocking it from that nuclear charge. Okay, going across a period. Okay, our ionization energy increases. Again, it can be really explained by the same trend as we use for atomic radius. We have an increase in the number of protons. As a result, that nuclear pull is much stronger, right? And it would be a lot harder to pull an electron away. So again, it's literally the same explanation, same shielding electrons, okay? And now let's talk about our not our last trend because there's metallic character, but our second to last trend, which is electronegativity. So as you go down a group, okay, the electronegativity is going to decrease. Again, guess what? Same explanation. We have an increase in atomic radius, okay, which means that there are more shielding electrons. And as a result, the ability of that nucleus to attract an additional electron is becoming weaker because the valence shell is much further away, and the bigger it is, the further away from the nucleus you are, the less positive pull that electron will feel. So more shielding electrons. Okay, and going across a period, I can't even fit my explanation in here, but hey, guess what? The electronegativity is going to increase, okay? And the explanation is exactly the same. Why is it easier for it to gain electrons? Because there's a larger nuclear pull, same number of shielding electrons, and so it's almost like a stronger magnet trying to pull an electron onto that atom, okay? So it's going to be, again, I'm just going to put these quotes that mean it's literally the same explanation, okay? So that leaves us again with our discussion of metallic character. And to kind of sum all this up and to finish things here, I do want to point out that that we also can kind of think about metallic character in the sense that, sorry, I was trying to get like a brand new color here for us, like something else that's not, there we go, that's not on the screen. Okay, for metallic character, which atom is most metallic? That's what I like to remember, and then that helps me remember the trend. So if we're thinking about an atom that is most metallic, remember that metallic character down a group, okay, metallic character, I'm going to abbreviate that MC, is going to increase going down a group. Going across a period, metallic character, okay, is going to decrease, which means that our most metallic element on all of the periodic table falls right here in this corner. Francium is the most metallic of all of our elements. And that, my friends, is the periodic table. The lesson is a little bit longer than I wanted just because of this review at the end. But again, I think it's really important to tie things up and to show you that as much as we separated these lessons, as much as we tried to, it seems complicated, all of the explanations are exactly the same. It's just about learning what ionization energy is, electronegativity is, atomic radius is, and then thinking logically about that and kind of trying to think all about that force of attraction. We're going to talk about attraction a lot in this class, and so it's good practice to start thinking about the attraction between positives and negatives now. All right, everybody, thank you so much. You have a fantastic rest of your day. I will see you tomorrow.